Okay, this subject is the Mohr circle. The Mohr circle is a very useful tool to visualize the stress state. Before we talk about the details regarding the Mohr circle, so now I'd like to remind you of the so-called stress transformation formula. The stress transform formula is what the first normal stress in certain direction can be written by the mean stress in 2 dimensions, and then the stress difference, the cosine 2 theta, and then plus shear stress, the reference shear stress tau xy, sine 2 theta. And then shear stress in that direction is equal to minus of the stress difference, and then sine 2 theta plus tau xy, the reference shear stress, cosine 2 theta. Here make sure that the mean stress is what? Mean stress is given by a half of the reference sigma xx and the sigma yy. And the stress difference, stress difference is equal to a half of sigma xx minus sigma yy. So here, what we want to do is we want to look at the structure of this equation, the first two equations, carefully. So if you move the first term in the first equation to the left-hand side, then I have a coefficient, a certain coefficient, and then I have the same coefficient in the second equation. And also, if you look at the second term in the first equation, I have tau xy, and also I have the same coefficient tau xy in the second equation. And these two coefficients are multiplied to cosine and sine. And then here in the second equation, we have sine and cosine. Then what's going to happen if you scale these two equations? So if you scale these two equations together, then I have sigma theta minus sigma, the mean stress square, is equal to sigma d square cosine square 2 theta plus tau xy square sine square 2 theta, and then I have cross term, isn't it right? So 2 sigma d and tau xy, and then sine 2 theta cosine 2 theta. Then let's look at the second equation. If you scale the second equation, the both sides of second equation, so we have sigma d square sine square 2 theta plus tau xy square cosine square 2 theta, and then I have cross term. It's not minus, it is not plus, and it's minus 2 sigma d tau xy sine 2 theta cosine 2 theta. Alright, so let's add these two equations together. Then what happens is the last terms are cancelled because their magnitudes are identical to each other. Only the sign is different. Sign is opposite. And then here, if you look at the first term, I have same coefficient. I can collect it. But here I have cosine square and sine square. Then cosine square plus sine square is equal to 1. This is a well-known formula, isn't it? And I can find the same situation in the second term. I have the coefficient, common coefficient, and then now I have sine square and cosine square, so they are equal to 1. So if you calculate the summation, then finally I have sigma theta and then minus the mean stress square plus tau theta square is equal to, then I have sigma d square plus tau xy square. So this equation is well-known equation. This is very similar to the equation of a circle whose center is placed at sigma m and tau is equal to 0. And what's the radius? This is the square of the radius. The radius square is given by the stress difference square plus tau xy square. Okay, so this is the derivation of the Mohr circle. This is a parametric representation of the stress state in different angles. So make sure that here, if you look at this equation carefully, so we have two theta component here. So which means any change in actual domain measured by angle theta, it corresponds to two theta difference in Mohr circle space. Okay. So here, let's take a look at an example. Let's consider an example here. Let's say I have my normal stress is equal to 10, and then my sigma y is equal to 5, and then minus 3 and minus 3 as a shear stress. And if you visualize this stress state, then it looks like this. This is my x direction and this is my y direction. So let's consider any angle. So first, theta is equal to 0. Then my new coordinate system look like this, which means my stress state is what? So I have 10 here and 10 here, and then 5 and also 5, and the shear stress was minus 3. That's why its direction, according to my reference coordinate system, this is the direction of minus shear stress. Okay, so look at this. The direction of positive shear stress upward in this side, but its direction is the shear stress is going down. That's why it's minus shear stress component as given in this exam problem. But let's consider 90 degrees difference. Say theta is 90 degrees. Then what happened then? My observation plane should be placed here. This is 90 degrees. And then because we use the right hand rule, it look like this. Then at that position, my normal stress sigma theta is equal to what? Sigma theta is equal to, here we have 5, and tau theta is equal to, its magnitude is equal to 3. But if you look at the direction, it is aligned with the positive direction. Then this is equal to 3, isn't it, right? So this is the situation what we have. So now let's try to calculate the detailed values, numeric values using Excel spreadsheet. So I prepared the Excel spreadsheet here. Then let's start from here. For example, let's remove this part. Okay, so initially when angle theta is equal to 0, then it corresponds to what? Sigma xx is equal to 10. Xx is equal to 10, and then my shear stress is equal to minus 3. So it is placed here. And then here 10 and minus 3. So 10 and minus 3. And then I consider 15 degree difference. Then starting from this point, and then we have angle change becomes 30 degrees. Isn't it right? 30 degrees. And then finally at this point, my sigma theta value is read as 8.17, and then my shear stress is 3.85. Okay, let's try to increase one more 15 degrees. Then if you do that, then I have one more point here. So my new value is here 6.15 and the minus 3.67. Okay, so it's changing counterclockwise. The actual direction is also counterclockwise. So if you choose the direction of shear stress axis upward, downward positive, then we're gonna have the same direction both in actual domain and then domain of Mohr circle. Okay, And then let's consider even more. If you consider, sorry. If you consider more angles, then finally we can obtain the nice circle as we discussed in that example. And then here I'd like to discuss a little bit more point here. And then let's look at this. So if you follow the Mohr circle, this is the starting point. And then from this starting point, no, 10, yeah, this is the starting point, sorry about it. This is the starting point. And then here the angle changes by the 15 degrees. In Mohr circle, it changes by every 30 degrees. And then if you follow the change of normal stress and shear stress in different angles, and then you can find at certain point the shear stress is equal to 0. The shear stress is equal to 0, and then the normal stress is maximum. That corresponds to the maximum principal stress value. And also, if you follow here, and here you can find the principal normal stress is minimum. At that point, shear stress is equal to 0. That corresponds to minimum principal stress value. And then the angle difference in the Mohr circle space is 180 degrees. In actual space, 90 degrees, orthogonal, isn't it? And then here, this point corresponds to maximum shear stress, okay, maximum shear stress. And then here, the shear stress is maximized, and then the angle difference to the principal direction is what? In Mohr circle space, 90 degrees, and actually 45 degrees. This is the characteristics of Mohr circle. Make sure the center of the Mohr circle corresponds to the mean stress value in the normal stress axis, and then shear stress is equal to 0, as I told you. And this is a brief overview regarding the Mohr circle. So if you have any questions, you may ask me. You may send me question. You may send me question mail. Sorry about it. Okay.